Okay, let's go ahead and get started. My name is Jeff Sale. Today we are going to see a presentation by Mahidar Tataneni. Mahidar is STSC's user support group lead, and he'll be telling us about the upcoming deployment of SDSC's new supercomputer Expanse. Before we get to that, I just want to point out Exceed. This is an Exceed webinar, and we like people to be aware of our code of conduct. Everybody is usually well behaved, but if you do observe any issues, please let us know at the appropriate time after the webinar is over. So with that, I will stop sharing and hand it off to Mahidar. Take it away, Mahi.
Thanks, Jeff. Let me get the share started. Jeff, I think you have to enable the sharing.
Oh, did I do that again?
And right on cue, we got a jet overhead.
That's right. Okay, so I just made you co-host. Sorry, that
Thank
should
you.
get me sharing.
All right, I think so. It should be visible now.
Yep, looks good.
And, okay. All right, let me get started. All right. So hello, everyone. I'm Mahidar Tataneni. As Jeff mentioned, I lead the user services group here. A lot of us have been working on Expanse out at STSC, trying to get things ready. And so I'll give a quick overview of the system today, where things stand, and like how do you get allocations and things like that. So the outline of the talk. I'll give a quick introduction of the system and an overview of all the components. And then we can dive into the system architecture details. It is going to be one of the first few systems to have the AMD ROM processors. So I'll go into the processor architecture details, the hardware details, and some of the applications that we have already tested. And we can't go into the results, but I'm going to basically give some broad information on how things are going. Expanse features a few innovative additions. So I'm going to talk about that next, and then the allocations process. So Expanse is basically a response to the NSF solicitation for advanced computing systems under the Category 1 capacity system. The PI on the project is Mike Norman, and Ilke, Amit, me, and Sean are co-PIs on it. It's a $10 million acquisition with operations on top of that. The primary vendor for the system is Dell, and the storage comes from Aeon Computing. And the compute interconnect and NVMe, basically we have components from AMD, Intel, NVIDIA, and Mellanox. So it's a mix of a lot of different features. So if you look at Expanse itself, basically it's made of 13 scalable compute units, and I'm going to go into details of the compute units in a bit. So it comes out to about 728 standard compute nodes and then 4 large memory nodes. In addition to that, we have 52 GPU nodes with NVIDIA V100 GPUs, 4 on each node. And this basically builds off the success we've had with Comet with a architecture like this. In terms of the data, we have a 12 petabyte storage file system, which is going to be based on Lustre. The aim is to have a bandwidth of 140 gigabytes per second and 200K IOPS. Just like our systems before, like Comet, Gordon, and Trestles, we have fast local SSD, local disk. So on Expanse, on the compute nodes, we will have the NVMe storage, and I'll have details of the sizes and all later on in the talk. We are going to be repurposing some of the Comet storage once Comet is retired into a 7 petabyte Ceph-based object store. So that's a new addition to the storage side. And in terms of what we are aiming this at, it's continuing what we did on Comet with the long tail of science support for a wide variety of scientific domains. Some of the innovative things we want to add on top of the existing science gateways, high throughput computing support that we already have, uh, is to have the options of cloud bursting and composable systems. And I have a slide on each of those. So let me go to the next slide. So a quick overview of the system itself. It's basically, as I mentioned, 728 regular compute nodes based on the AMD EPYC ROM processor, 64 cores per socket. So it works out to 93,184 compute cores. So that nearly doubles what we have on Comet. So in terms of just the core count itself. And then we're going to have 52 four-way GPU nodes based on V100 GPUs with NVLink connectivity for the four GPUs on the node. And we've been running benchmarks on some test clusters that we've had access to. And based on what we've seen with early application performance, we expect to easily go over 2x the throughput of Comet. And there's per core improvement over the Haswell, and we also have nearly 2x the core count. So in terms of users moving from Comet to Expanse, we kind of expect a smooth transition. We will be doing some training for users in coming months. We've already compiled and run many of the common software packages on the ROM-based clusters, so we're fairly confident it should be a smooth transition. In terms of where things stand, system is currently being built at the Dell's facilities, and I think the delivery is planned sometime in July. It is available in the current open extract window, so if you're looking to apply for time, Expanse will be an option, and I'll have some details, which will be reviewed in the August meeting, and then you would have production in October 1st, so that's when the allocations would start. So like Comet, which is going to be retired in March of next year, Expanse is essentially going to look at a broad-based approach to a huge number of scientific domains. If you just look at Comet, we've had 40,000 plus unique users, over 1,000 publications, 2,000 plus research, education, and startup allocations, over 400 institutions, and lots of discoveries and breakthroughs enabled by Comet. And in terms of operations, there's going to be a 6-month overlap between Comet and Expanse, so it should provide an ample transition time for users who are already on Comet. So going back to the outline, so let's look at the system architecture. And I try to make my cursor larger, so hopefully I can point things out. So as I mentioned, you're going to have 13 scalable compute units. So that would be a rack like that. Each of the SCUs will have both CPU and GPU nodes, and I have some details down the road in the talk. And what we've done is basically designed it such that we have 100 HDR 100 to the nodes in a rack, and there is a HDR 200 switch for each rack. So if you work that out, you will basically have a full bisection at the rack level, which on Expanse is a lot of cores. You have nearly, I think it's 7,168 cores, if I have the math right, per rack. So that's a pretty big chunk of cores that will be basically full bisection bandwidth. And then between racks, there's going to be a 3:1 oversubscription. So in terms of the overall numbers, basically, we already looked at the core count. It's about 200 terabytes of memory total. And into the large memory nodes are going to be 2 terabytes each, and a 12 petabyte cluster file system, as I mentioned. And that's going to be InfiniBand connected. And there's a network diagram a little later. Uh, the compute racks are direct liquid cooled, so that's a new thing at STSC. So it should improve on the performance side and help us with the cooling, I think. So all of that basically composes the system. So the SECU is essentially designed for the kind of mix that we have. Basically, you have 56 CPU nodes in each SECU, and then you get 7,168 compute cores. So if you remember on Comet, we have a 1728 core job limit, so we can bump that up on Expanse to 4,096 cores to keep a power of 2. And that actually gives us more coverage in terms of the type of applications that can scale out, and even within a rack. And in terms of the compute node, basically, as I mentioned, it's a AMD EPYC 7742 processor, which is at 2.25 gigahertz with a boost that goes up to 3.4, I think. It's a PCI Gen 4 interfaces, and you have 256 gigabytes of RAM on each node. And I think there's a correction here that should be 1 terabyte NVMe on each compute node. On the GPU nodes, you have basically V100 nodes, and you have 4 of these GPU nodes in each SCCU. And it's 32 gigabyte of memory on the GPU and 1.6 terabytes of NVMe. That one's accurate. It's on each GPU node. And the GPU nodes are going to have Intel, I think 6248 Xeon processors with 20 cores each. So you're going to have 40 cores per GPU node. So as I mentioned, since you have 56 compute nodes and 4 GPU nodes, that's 60 connections going into the HDR switch. And if I think it's a 40 port, so you end up with basically 10x of them going out to the second level. So you get the 3:1 over subscription. So in terms of network connectivity, STSCs kind of always had pretty good connectivity out of our center. On the Prism Campus DMZ side, between 10 and 100 gigabits per second, going to the Open Science Grid resources and the CAV-IT2 resources. And then on the external network, we are on the PRP, on Internet 2, Scenic, and the Exceed network, and some direct connectivity to Amazon. So that's like a brief overview of the system itself. In terms of the processor, before I go on, maybe I should check if there are any questions in the chat. So, Jeff, do you see any?
Yeah, there were a couple actually. One was, are the V100s V100Ss?
This SXM2.
And then does the scheduler allocate jobs on a per node basis for the CPU nodes?
We will have a mix just like Comet. So we would have some nodes which will allow shared, and then some nodes that will be exclusive, and we can have an overlap between those two partitions. I think that's what we've done on Comet, and we would have the same thing on Expanse. I mean, the one question there would be, and when I go into the processor architecture, you'll see is there a different unit in terms of within a node, at what level do we allocate? Do we go to a core count, or do we go to one of the CCX units on each chiplet? So that's a question. I mean, that's something we'll be looking at, but yeah, we will have shared queues. Okay, let me move on to the processor architecture. So it has, the processor has 8 core complex dies. So this is with 7 nanometer technology. So each of these dies has 8 cores, and I'll look into the architecture in the next slide. So these 8 So each chip has 8 of these CCDs, and so on Expanse, since it's fully populated, you're going to have 8 cores on each, so that's 64 cores per socket, and it's 2 sockets, so you end up with 128 cores per node. And the CCDs connect to the memory and the I/O through the I/O die, and there are 8 memory channels per socket, and it's DDR4 memory at 3,200 megahertz, so 3.2 gigahertz. And it's PCI Gen 4 with up to 128 lanes of high-speed I/O. And the memory and I/O actually can be abstracted into separate quadrants, each with 2 DIMM channels and 32 I/O lanes. And this kind of gives you options as far as the NUMA domains go. And I'll talk about that a little bit further into the talk. So then each of the core complex dies, as I mentioned, has 8 cores. So that's basically split into 2 core complexes, which CCXs per CCD. So there are 4 Zen 2 cores on each CCX, and they share a 16 meg L3 cache. So if you can do the math, basically, since we have 4 of these, 8 of these CCDs and then 2 core complexes, so you end up with basically 16 in each socket. So 16 times 16 gives you basically 256 meg of L3 cache, which is quite nice. And then there is, each core has a private 512 kilobyte L2 cache. So, and this will, I mean, obviously have considerations when you're running jobs, and especially hybrid jobs with MPI and threads on how you bind things. And I'll talk about that a little bit later on. So that's kind of the core component, the 8 cores in a CCD. And then this CCD basically connects into the I/O fabric there. So once you have the CCD and you know that you have 8 memory channels, there are several ways you can actually split that up into NUMA nodes. So there are 4 logical quadrants that allow the processor to be partitioned into different NUMA domains. So the options are set in BIOS, so it's a reboot if you want to change it. But in this case, I think for this setting at least, we probably wouldn't be changing it, because it's for an HPC kind of workload, you have 4 NUMA domains per socket, and that works fine. Because most HPC codes can be NUMA aware, and you can always give users help with the binding aspects of things. So these domains are designated as NUMA per socket. So NPS 4 would mean 4 NUMA domains per socket. So that's basically the quadrant I was talking about. So you would basically have two CCDs in each quadrant. That's 16 cores and the 2 memory channels. And then how you manage the NUMA domains goes next. So one configuration is an NPS 1 configuration, where you take all of this and put it in one single NUMA domain. And memory just gets interleaved across all 8 memory channels. This is something you can try if your workload is not very NUMA aware and can't deal with the complexity of having too much detail on the NUMA side. So you just have one such thing, and you can bind to one domain essentially. NPS 2, you essentially partition into 2 NUMA domains. So half the cores and half the memory channels, so 4 memory channels connected to the processor, are in one NUMA domain, and the memory is interleaved across 4 memory channels. So NPS 4 is what is recommended for HPC configuration. So the processor is partitioned into 4 NUMA domains. So each logical quadrant is a NUMA domain. So you would have 2 CCDs and 2 memory channels. And this is what you'll see if you log into one of our test nodes right now. Is basically memory interleaved across 2 memory channels. And the PCIe devices will be local to one of the 4 NUMA domains. The I/O die that basically has the PCI root for the device, which includes the InfiniBand network card. So So that would be local to one of the four NUMA domains on one of the sockets. So this is the typical HPC configuration, and the workload is NUMA aware. So hopefully we can pin the ranks and memory to the cores and the NUMA nodes that are defined. So in terms of what we've done, we've kind of tested this for a few months now. We tested with AOSEC compilers, GNU compilers, and Intel compilers, and Intel compilers work fine. And the MPI versions, we've tested MBAP-ish2, OpenMPI, and Intel MPI. Some specific optimization flags is basically Zen version 2 for the AOCC and GNU compilers. For Intel, you just do a core AVX2. And it was pretty painless to actually port the codes and make things run. A lot of our tuning work was more to do with the BIOS settings to use and things like that. But in terms of running, it was very similar to what we are already doing on the machines. So the runtime considerations, of course, you do need to be aware of the mappings, and if you're doing pure MPI, do a mapping by core, say for example, and use various options with the MPIs like map by core or pin domains and things like that. With OpenMP, you can use affinity options. The tricky part is with the hybrid codes where you have hybrid MPI and OpenMP, or hybrid MPI and P threads, which is especially if a code is not doing this actively and the threads are moving around, you could lose performance if you jump around that way. So you try to keep the threads on the same NUMA domain or CCX as the parent MPI task. And you can use affinity flags, or in the case of the hybrid MPI P threads, we just wrote a wrapper script which uses task sets to place the threads. So this is what we use for XML, for example. I mean, obviously, there are a lot more optimization considerations, and I'm sure some of you have a lot more expertise than I or others. So I'm sure we'll be talking a lot about this down the road and have more detailed presentations and workshops. So in terms of what we have run, we took some of the standard applications that are running on Comet, and we've had these benchmarks for various job sizes, going from single node. Actually, since it was Comet, we kind of had a reference of 24 cores, 48 cores, going up to I think 768 cores. Which on this machine, actually, it's not a lot of nodes. So it's interesting. So with 6 nodes, we get there. But we benchmarked basically the CPU applications on Chromax, NAMD, Neuron, OpenFOAM, Quantum Espresso, XML, WRF, and Astral. And this was a mix of different types of cases like pure MPI, hybrid MPI, OpenMP, hybrid MPI, and P threads. And we kind of tried all different compilers. So, I mean, the early results just from the test clusters, and I'm sure there's a lot more optimization to go, show performance. Basically, we can easily match on per core basis to what we get on Comet. And on the high end, we can get nearly 1.8x faster on per core basis. It kind of depends on the application, the network requirements, and things like that. So overall, for most cores, we were kind of seeing improvements between 1.2x and 1.4x on a per core basis. On top of this, you kind of have almost 2x the cores. So we expect the throughput to be easily more than 2x of Comet. So as the hardware comes online at STSC, we'll obviously do much more and share more results, actually. So let me see. I'll go into the GPU node architecture, and then maybe I'll stop again for questions. So on the GPU nodes, we have 4 V100 GPUs per node, and these are 32 gigs SMX2 GPUs. There's 384 gigabytes of RAM, 1.6 terabytes of PCIe NVMe, and two Intel Xeon 6248 CPUs. We actually have one of the production nodes, I think, in the test cluster right now at SDSC, and I just grabbed the topology of it. So you can see NVLink, two hops of NVLink going between the various GPUs, and uh, basically, and then the InfiniBand card. So maybe I stop here and see some more questions. I see 26 notifications, so I'm assuming there are questions. Jeff, if you could.
Yeah, Marty's been handling some of them. I'm just trying to see if there's
Okay.
anything that he hasn't covered. Marty, do you want to jump in?
Yeah, sure. I mean, I think one that Kenneth had was in terms of the binding and mapping, are we going to sort of do a rewrite for the IB run wrapper for the system?
Yeah, definitely. I think we have to do that, and we probably will add another script so that the affinity part is also done with the scripting, because it can get tricky, especially with like task sets and if you're doing the MPI threads kind of combinations. Okay, so I'll go forward with the software stack. So we will continue to support like a broad application base, so like all the commonly used packages in bioinformatics, molecular dynamics, machine learning, quantum chemistry, structural mechanics, visualization, and it's not the whole list, and there's a lot. What we essentially started out doing was take the current application stack on Comet, and we're replicating all of it as a starting point. Uh, uh, and we will, as I mentioned, have upcoming webinars and tutorials to help Comet users transition to the Expanse application environment, and you'll see more of this. One change is we're basically doing SPAC-based installs, and it's been pretty interesting getting the entire stack spun up with SPAC, but looks good so far in terms of replicating the stack. And all of us in the user services team have been kind of working through these. We'll continue support for singularity-based containerization, and so you would have all those options that you see on Comet. So one other new thing from the user side, so you would have a Expanse user portal that will come online when the machine comes up. Basically, it will leverage Open on Demand to provide browser-based features. So some of the features that that are part of Open on Demand, and we've been working to get them kind of set up in our environment, is to have like job and queue information, user settable reservations, some of the documentation and support tasks can be in there. Remote visualization, and I know this has been something that we've often get asked in Comet, so that's going to come through this and should improve things quite a lot and reduce the work needed to use some of the remote visualization. Like you don't have to install a bunch of packages on your client machine. You can go through the OOD based Expanse user portal. So this, and then we could have support for Jupyter notebooks through this, and do some basic file management and job templates for commonly used software packages, so that you can launch jobs easily with a low barrier to access. So next, I want to go into some of the Expanse innovative features. So we've done some of this work on Comet and on other machines at SDSC. So one of the things we're going to feature is integration with public cloud. Now this, I should stress that this is for people who already have access via other mechanisms to the cloud. So it's not, we are not providing cloud resources. We are just enabling somebody who wants to integrate their runs on Comet with the runs on the cloud. So basically, the way it works is to use Slurm and some in-house developed software and Terraform. And we've been testing this with the Cypress Gateway. And I think that was funded a little bit internally, and then also from the NSF ECAS Internet 2 project. where we were bursting out to the cloud. And I think Trevor has a nice talk on this if people are interested. So the approach is cloud agnostic, and we'll try to support major cloud providers. And users will submit directly via Slurm or as part of a Compose system. And we'll be looking into options for data movement, data in cloud, remote mounting of file systems, cached file systems like Stash Cache, and data transfer during the job. The other piece that we are going to bring on with Expanse is a composable systems. So if you have a complex workflow that needs resources beyond what's available on Expanse, but you want to integrate all of it into one composed system, we are looking into making that feasible. So on Expanse, we'll be managing the system using the Bright Cluster Manager, and with its CM scale feature, we should be able to provision nodes between Slurm and Kubernetes-based cluster. So and that's kind of the building block for this, and then we're going to look into expanding that beyond the system on-prem. So the requests for I mean, this obviously involves quite a bit of work. It's not something you can just log into the machine and submit and run. So requests for something, some people who are interested with this kind of feature should be part of the extract request and mention it in your proposal. And also contact us if you're interested, so that we can look into the feasibility and what are the options. And we can provide some advanced user support resources for that aspect of it. This is part of our operations funding for the project. So that should be an exciting thing to kind of pull in other resources like FPGAs or some edge computing and other options. So with the system, I mean, obviously there's going to be a lot of user support training, outreach, and education. So we can users can make use of the system efficiently. It's going to be fully integrated as an Exceed level 1 resource. So just like Comet and other systems at NSF funded systems at STSC. Overlap of 6 months in the operation. So that gives us plenty of time to train users to transition from Comet to Expanse. We'll start it off with some events in September, but we'll likely do more of them so that people can transition from a Comet to Expanse. We are going to be launching a new program with this for HPC at MSI, targeted at minority serving institutions. This essentially will make use of discretionary time, so we can award time to PIs at MSIs via a rapid review process, and can help them get on the system in a much quicker way. And as I mentioned, advanced support will be available from staff for cloud integration and composable, but it does need to kind of be accounted through the Exceed process. And we will kind of be working with Exceed and Extract to develop some criteria for the innovative elements. So that brings me to the allocations piece. So Expanse resources can be requested in the currently open Extract period. So it's already open June 15th through July 15th. And this is for allocations that start October 1st, 2020. So I have the link there for the submit request for the allocations. And this is a general link for all Exceed allocations, just to be clear. And when you click on it, you have to log into the portal. If you don't have a portal account, you can self-create that. And there's a link on the portal for creating the account. From Expanse, there will be 3 resources, essentially the Expanse compute, basically for allocations on the compute part of the system, the AMD ROM part of it. Expanse GPU for allocations on the V100 GPU part of the system. And Expanse project storage. This is allocations on the Expanse project storage space. This will be available on both the GPU and the compute part. The total space we are targeting is around 5 petabytes for this, and remember this is spread out over all the years. So, and this will come out of the 12 petabyte cluster-based file system that we'll split between projects and Scratch. And so the Scratch area will be larger to allow for larger writes during a simulation, but it will be actively purged for based on a policy. And so overall, this actually roughly doubles what we made available on Comet for project space, which kind of is in line with the doubled compute capacity. So if you go to the allocations page and go to click on the submit request page, you will see the login piece here. And so that's the submit review request button. And if you go further, when you're doing the submission, when you get to the, you have to fill out some of your personal information regarding CVs and things, title of the project and so on. And then you have the resources tab, and Expanse is an option on them. So you'll see Expanse Compute, the Expanse GPU, and the storage under the storage tab. I kind of broke this out. It's in one long line if you are actually filling it out. So in terms of important dates, so like I said, the submission period is open. So we suggest that you apply for time on Expanse during this period. Just for reference, Comet typically used to make available 80 million core hours on the CPU side. Since there's only 6 months left from October for Comet, it's going to be down to 40 million. But on the Expanse side, we'll be spinning up 170 million SUs available. So overall, it more than doubles what in terms of what number of SUs are available. And the review will be in August and starts October 1st. So right now, we kind of looking forward to the hardware delivery, installation, and then application stack development. We will have an early access period, September 1st through September 30th, so the whole month of September, essentially. And related to that, we'll have training for people who want to transition from Comet to Expanse. We'll have an Expanse 101 later in September for accessing and running jobs. And then the production period in October 1st. So I think that's a quick overview of the machine. Maybe I'll go through the summary and then we can stop for questions again. So overall, Expanse will provide a huge increase in performance and throughput compared to the Comet machine. So more than double. And as I mentioned, you would expect about 20 to 30% improvement in per core performance for most codes. And some go higher, some go lower. The Expanse basically is an evolution of the Comet design. So, and we are adding in innovations in cloud integration, composable systems, and we're going to continue supporting all the stuff that works, like the Science Gateway support, the distributed computing via OSG, and all that's already happening on Comet. So in terms of early access, we will have communications upcoming with further details. As soon as hardware lands on the floor, we're going to have a lot more detail coming, basically. And you can follow all things Expanse at expanse.stsc.edu. And looking forward to people coming online and testing the machine. So thanks. I'll grab the rest of the questions now.
So Mahi, yeah, just since I'm familiar with the questions here, there's a couple of questions on allocations. Do you know if the sort of educational allocations or startup allocations can be applied for right now?
Right now, they're not active. I think what they will be as soon as we are up with the machine. So right now, it kind of doesn't make sense because the machine's not.
So it's only
available.
research allocations.
Yeah.
Another one related to allocations was if they're, say they have a research allocation right now, can they submit a supplemental for Expanse?
Yeah, definitely. I think that's an option. But again, that would be when the machine's available, right? Yeah, but that would definitely be an option. And I forgot to mention basically, uh, uh, I think in the current allocation window that allocation meeting that just ended, we made full allocations on Comet. I think 80 million core hour, actually closer to 90 million core hours. And a similar thing on the GPU side, we made a full allocation. And since they're only 9 months, the remaining time on those allocations will also go on to Expanse.
So essentially, yeah, the users that when Expanse is deployed and in production, they can do transfers over.
Definitely, yeah,
Yeah.
yeah, and I think transfers or supplements are all welcome.
Yeah. Another question is about benchmarking results. I guess when applying for an allocation, should they use their Comet results? And
Yeah, I think at this point I would say using Comet results is a good stand-in. I think, yeah.
Okay.
That would be the I would say that would be the lower end of the performance, so it's not a bad stand-in for it.
Okay. I mean, I think I know the answer to this, but you mentioned the 40,000 unique users. Does that include gateway users? I think that's true.
Yeah, yes, it does include gateways.
Another question is on virtual cluster support. That's probably I mean, it's a little bit tricky. I think we're going to have right the Kubernetes aspects available on Expanse for sort of select users that sort of have the sort of extended collaborative support services through Exceed that sort of have the time and energy to devote to that.
To
So in
devote to that,
theory,
yeah.
you can do something similar, but it's a bit heavy lifting. But if your research group needs that, that's
Yeah, I
something
would say that's a fair
possible.
thing to say. Yeah.
Let's see. Uh, Igor asks about how will we be integrating with the Open Science Grid.
That's a question for you, right?
I guess. So Igor, I mean, just to start off, essentially, we're going to be another site on OSG. So we can talk more offline about that. Because yeah, there's some other ideas of things that we might do. And then John here asks, what about using Stampede 2 KNL results for scaling performance numbers, I assume, when submitting their research allocation proposal?
I would say that may not be a fair thing,
Yeah.
especially when you go to multi-node. And the reason I say that is if you look at the bandwidth, I think the KNL cores are probably half the frequency, I think, right? And so these are, 2.25 gigahertz cores, and they don't clock down too much, even when all 128 cores are in use, and when you have uh, the AVX2 enabled. So I would think you would get a lot more performance per CPU core, which means that you might get network limited because the network bandwidth is 100 gigabit. So it might not be a straightforward one-to-one with the two machines there. I would be a little hesitant. Like if you're looking for kind of a window in terms of per core performance, I would say you would see something between Comet and I think maybe the Skylake nodes on the. We'll probably match the Skylake nodes on most of the codes. So, but yeah, I think the KNL might not be a good comparison. Like you might scale better on the KNL just because the CPU codes are, the cores are slower, is what I'm trying to get at.
So the next question was in terms of when making the request for GPU hours, right? Comet has two different types of GPUs. So is one SU on Expanse one V100 GPU hour?
Correct. Yeah. Since there's only one type of GPU, we're just going with the V100 GPU hour. And I think for that, you may have some options. I'm sure there are V100 resources. I think PSC already has some. So you might have some way to get V100 performance, essentially.
I don't see any other questions for you right here. So
Sounds good.
Yeah, I mean, we can wait a minute or two to see if there's any other questions.
Yeah, we can
I'm just
give it a
answering one
couple of
in the
minutes.
chat.
And Marty, this is Amit. I think there is a question about the end of life for data OSs.
Oh, that's a good question. So yes, so the data OSs basically goes away when Comet production ends, which is basically end of March next year. So do start planning for data movement. And we will essentially, that's one of the topics we will cover in the training, in the transition training. Because obviously the Expanse file system is brand new, separate from data OSs. So users will have to move data that's needed. And also, as I mentioned, the data OS's storage is being repurposed to form the Ceph-based file system that will be available on Expanse. So you probably, I mean, we will give a little bit of grace period, but it's not. It's going to be pretty short after Comet retires. So.
Hey, Mahi.
Yep.
Here's another question asked earlier. Will one be able to manage the 4 NUMA domains, e.g. using acetyl NUMA control?
Yeah, you can use NumaCTL, I'm sure. Yeah. Yeah. But a lot of the MPIs already kind of have things integrated. So like HTTP lock based or some other mechanisms to basically pin. So, but yeah, definitely an option.
Then I'll bring up a fun question. Somebody asked, when was the last time we had a liquid cool system on the machine floor at SDSC? Our theory is it's the Cray T90. I thought
probably, yeah, that's my guess. Certainly not in my time. So, and I've been here 15 years. So I haven't seen a liquid cooled system. So, but of course, this is there on other Exceed systems already. So.
I think we've answered all of them.
Okay, great. Thanks everyone for taking the time to listen to the talk. And we are really excited with the machine coming online and definitely be communicating as things go up, basically.
Yeah, thanks very much, Mahidar. That was excellent. Very exciting. We will be making the recording and the contents of the chat available after the webinar. It might be a day or two once the recording and the transcriptions generated by Zoom. So thanks everyone for joining and have a great rest of your day. We'll call an end to this meeting.
May I ask another question?
Sure, yeah.
So,
sure.
So after Comet retire, is that like end March or end April? So if we still have leftover SUs allocated in Comet, so what will be the conversion rate if we transfer?
Oh, yeah. So that's something we probably will have to work out based on the application performance. So we will, yeah, that's one thing that hasn't been, I don't think there's a number in the converter yet.
Yeah,
but,
that's something we can maybe.
Yeah, we can, that's something we can.
I think we know this is an issue. We have to sort of come up with a mean value from our benchmark. results.
So one thing to note is, AMD-based systems are coming up across the Exceed landscape. So we kind of need to make sure things are consistent across. And so this will need some discussion before we come up with a single number.
So my ITSA gateway takes around 11 billion SUs per year. So what's your suggestion for SU application for our renewal this year in October? Oh, no, sorry. Yeah, October 1st.
So I think if I recall right, you're doing basically single node runs, right? And,
yes, mostly.
And so I think my guess is it's going to be like I think you should use that as the baseline, but you probably can do with less SUs. But to be safe, I would say just use that as the baseline, the same number as Comet.
So we should directly apply for Expanse, or should we apply like half Comet, half Expanse, and then?
I would say apply for half and half, because if you have unused SUs on Comet, they can be moved to Expanse later. So
okay, so for
that
us,
gives you enough time to kind of transition in a easy way.
So that means around 5 million for each.
Correct. Yeah.
Okay.
Okay, I guess that's it. Thanks very much, everyone.
Thank you.